Okay, this is a lesson on electrolysis. We'll be able to calculate the current needed in an electrolytic reaction, along with the time that is needed, and then the mass of the elements that we can produce in that electrolytic cell. We'll be able to identify the parts of the electrolytic cell with 80% accuracy. A reminder that your quest on the Nernst equation, that was the last play posit that's due on Tuesday night. And the quest for this lesson is due on Thursday night, on the 12th. Your lab report is due on Monday, so do not forget. Okay, so electrolysis. The biggest issue with electrolysis is units. So I'm going to talk about the units a little bit. There's really one equation we have to use, but it's all an application of what we've already done. We know voltaic cells, your galvanic cells, are all spontaneous. So when we're talking about electrolysis, we're pumping electricity through a non-spontaneous reaction. So we were asked before to clarify between spontaneous and non-spontaneous. So with spontaneous, you have a positive cell potential and a negative delta G. With non-spontaneous, you have a positive delta G and a negative cell potential. So the only way to get that reaction to run is to give it a power source. The equation we're going to be using for calculating electrical energy of electrolysis, it's the number of coulombs of charge, so number of coulombs, and it's equal to I times T. T is your time. So we've got our time. And then I we use for our current. So current has units of amps. We'll talk about that in a second. But they use I instead. And that's based off of Faraday's law. It's a physics thing, physics and electromagnetism thing. So they use I for that. I believe, correct me if I'm wrong, I believe inductance is what they use that for, so it's I. When we get into units, remember that a volt has units of joules per coulomb. That part is very important. We also know that amps have coulomb per second. So we have 1 coulomb of charge being transferred per second. That is what an amp is. So talking about our current there. With Faraday's constant, that's our 96485 coulombs. No, I spelled coulombs wrong, sorry. Coulombs per mole of electron, so mole of electrons. So all those units will be able to cancel out when we use this equation. We just have to do a little work to get there. One of the things in an electrolytic cell is that there's still an anode and cathode, but the charges switch. If we think about it, this makes sense. We're doing an opposite process, so the charges should switch because we are causing the anode and cathode to move in different directions. So we've got the positive anode and a negative cathode. So we use EPA, electrolytic cell, positive anode. When we predict products of electrolysis, there are a couple of different situations we'll be looking at. We have situations that are in water and situations that are not in water. If we just have an ionic compound and we're trying to plate it out and get the metal back, the cation will be reduced and the anion will be oxidized. If water is present, that's where it gets a little bit trickier. We're going to have to balance our half reactions. These reactions are usually done with platinum electrodes, so they're inert because of water. So as a result, there are times where the water could oxidize or be reduced over the metal that we are trying to plate out. So we have to pay attention to the cell potentials for that because that will help determine whether or not something will plate out. So we'll need to figure out if the ions are reacting or if the water is reacting. As a general rule, group 1 and group 2 metals, that's your alkali metals and your alkaline earth metals, We know that those things are typically soluble, therefore they will stay soluble. Water will be reduced over those things. Same with polyatomic ions. It's hard to oxidize an ion and strip them of the electrons because they're already very stable with those extra electrons. So then with water, water will be oxidized instead. These two half reactions are really important. These are in your table. This one is flipped on your reduction potential table because obviously it's for a reduction half reaction. I just reversed it for you so you can see what it looks like when it's oxidized. If we think about what oxidation is loss. If you look on your product side, you've got electrons on your product side, therefore we know electrons are being lost. We also see that our H now has a charge. If we lost electrons, we become positive. So that's how we know that this one is for the oxidation reaction. If we're looking here on the reduction one, we see electrons on the reactant side, meaning that they're being gained. And if we look here, the OH is being reduced, so the OH from water is breaking off and it will be reduced, so we are reducing our charge. We do get a negative charge, and therefore that's how we know this is the reduction version of this reaction. So these are on your table, just keep track of them because they will be of good use in these type of problems. Okay. This is a great little chart. I would pause here and just jot this down. It's very good at the comparison here. I talked about the electrodes already. It's inert electrodes usually for electrolytic cells. Something that's different is that it's in one compartment versus 2 compartments for a galvanic cell. We know that it's not spontaneous, and we know we need a power source. And I briefly said delta G is going to be greater than 0. That means it's not spontaneous. We want to pay attention to the charge here. You see, compared to here, the charge has in fact swapped. The anode is positive, and the cathode is negative. Okay? But we still have 2 electrodes. We still are in some sort of vessel that's conducting. The salt bridge disappears. That's a galvanic cell thing. And you can study up on galvanic cells later, but I really want to just jump through these examples. Okay? All right, so our first example, how long must a current of 5 amps be applied to a solution of silver plus to produce 10.5 grams of silver metal? So before we even start, I want to remind ourselves of our units. You know, amps have units of coulomb per second, and we know that our equation, the number of coulombs C is equal to the current I times the time. Something I didn't tell you before, but I should have said, is that the time is in seconds for this to work, hence why we have our unit of coulombs per seconds for our amps. So, unfortunately, there's no real way to use that grams right off the bat. So, you guessed it, what should we do? Let's convert our grams into moles. So, we want to know how long it takes to make 10.5 grams of silver. We convert that to moles. We need moles of silver on top. And I'm going to pause for a second. Every time I do problems like this, dimensional analysis is key. I know some of you are really good at just doing the math in your head, but please, please, please make sure you use dimensional analysis, because we're going to have complicated problems later where it's really going to mess us up when we start thinking, trying to think in our heads and do it mentally, when we really need to make sure we understand where the units are going and how the units are canceling. So with dimensional analysis, the idea is I'm multiplying by a fraction. Anytime I have a unit I want to get rid of, it is on the bottom of my fraction. So I want to get rid of grams. So I'm using the molar mass of silver. Molar mass of silver is on the bottom, and then I'm going to moles. So anytime you pick a new unit, that unit is on top, and I'm going to moles of silver. Now, if you're familiar with fractions, multiplying by 1 over a number is the same as dividing by that number. So yes, you are dividing by the molar mass, and you may be familiar with converting grams to moles by dividing by the molar mass. But if we use this format, we can keep track of all of our charges and our moles and everything that we need. Okay. So now we're in moles of silver. The issue is we need to figure out how many electrons there are that we need in order to figure out our coulombs, right? This is the only thing we can find right now. We want to know time, that's our X, and we have our amps, that's our I's, that's 5 currents, or 5 amps of current, so we need to figure out how do we get our coulombs. Well, we know coulombs is, Faraday's constant has a unit of coulomb over moles of electrons, so we need to be able to get to moles of electrons in order to get back to coulombs, okay? So, that being said, this is where our balanced equation comes in. Remember that this is technically a 1 in front of here and a 1 in front of here. I have moles of silver because my grams have canceled out. I'm now in moles of silver. I want moles of silver to cancel out, so I'm going to use that coefficient of 1 next to my silver, and I want to figure out how many moles of electrons I have. Well, the good news is you can use your balance equation here to do that. I have 1 mole of electrons for every 1 mole of silver. Now I'm in moles of electrons, and I can get back to coulombs. I know that 1 mole of electrons is equal to my Faraday's constant, 96485 C. That is your coulombs. And we can go through and do that math, and I'll even cross things off for you. Grams cancel, moles cancel, moles cancel, moles of electrons, and we'll be left in coulombs. So let's go through and do that in our calculator. So we've got our calculator here. So we've got 10, let's make sure it's on, 10.5 grams times the top of our fraction divided by the bottom of our fraction. I always put parentheses around it. So 107.87 is my molar mass times 1 over 1. So I got 1 mole of electrons and 1 mole of silver, and then Faraday's constant 96485 divided by 1. And then get this number 9,391.79 coulombs. I'm not going to round yet because I want to save my sig figs for the end, so we're not going to really round that. Really we'll just truncate. I'll truncate at 7.9. So we'll go back here, we get 9. Let's go back to purple. We got 9,391.79 coulombs. I didn't round, I just truncated. This is what we are going to plug into our equation, the C equals IT. All right, that part's fairly easy. So we've got 91.79 coulombs. This is our C. Then we've got I times T. We've got 5.0 amps times T. How are we going to solve? All right, let's rearrange. 9391.79. This is just a 1, sorry. Coulombs over my amps, which is 5.0. Remember that the units are going to be coulombs over seconds. Coulombs are going to cancel out in this case, and we'll be left with our seconds. So we'll go back that number divided by 5. And we get 1,878.358 seconds. So 1,878.358 seconds. Now we want to do this in sig figs. Let's check. We got 3 sig figs here, 3 sig figs here. Our answer should be in 3 sig figs. But the issue is seconds is way too large. We need to make sure that this is an answer that we can grasp in a reasonable amount of time. Let's go ahead and throw this into minutes. We know we've got 60 seconds per 1 minute. So essentially we're dividing by 60. I just continued with my dimensional analysis to put it in that form. And when I divide by 60, I get an answer in minutes, 31.305, but I want 3 sig figs, so I'm just going to do 31 0.3 minutes. So this reaction, if I wanted to get 10.5 grams with this amount of current, would take me about a half hour. Okay. All right. Next one, calculate the amount of time required to produce 1,000 grams of magnesium metal by electrolysis of molten MgCl2 using a current of 50 amps. All right, so this is a fun little one. We have to pay attention to some of the keywords and to the half reactions here because we need to look at our electrons and make sure everything's balanced out, which it should be. Keyword here is molten. If it's molten, you got to go back here. If it's molten, we're looking at this section here. If you have a pure molten compound, the cation will be reduced and the anion is oxidized, right? So in this case, it is molten, there's no water, Mg is going to be reduced. So we just need our magnesium half reaction. Mg2 plus will be reduced down to magnesium, and it has 2 electrons. We know that Cl minus is 1 electron each. If we were to balance this whole equation, we still would end up with 2 electrons. I'm going to skip that step for now, but there are other problems where you can't skip that step. So just be aware that if it's not ionic, or if you are dealing with water and trying to figure out the oxidation of water or the reduction of water, you will have to balance the entire thing. Okay? So here's our starting point. We have 1,000 grams of magnesium metal. Same deal as last time, except this time our moles of electrons are going to change. So what should we do with our grams of magnesium? Yep, convert it to moles. I'm going to moles of magnesium, so that's on my top. Grams, the molar mass of magnesium is on the bottom. Those things will cancel out. I know for every 1 mole of magnesium, how many electrons do I have? 2 moles of electrons. Yep, using the balanced equation just like last time. And then I use what number? Faraday's constant. All right, 96485 coulombs per mole of electrons. Okay, and I can go through and do my math again. So I'm starting with 1,000 times 1 over 24.31, close parentheses, times the 1 mole of magnesium, but we started with the 2 moles of electrons. So 2 moles of electrons on top divided by 1 mole of magnesium from our balanced equation, and then times Faraday's constant, 96485, divided by 1. All right. And we get this huge number, which I'm not going to round. Again, I want to keep sig figs involved. So in the end, we should have, I guess, only 2 sig figs in this problem. Yeah, I guess we'll go with 2 sig figs in the end. So this equals 793,788.5.644. What unit is that? It's coulombs, right? Coulombs, and that's equal to my 50 amps times my time. If I go ahead and divide that number by 50, I will get my time. And I get T is equal to 158757.75. What's my unit? Seconds. That is 100, almost 160,000 seconds. That is not a useful unit for me, right? Think about this. We're trying to apply this in real life. I need to figure out how much time realistically this is going to take me if I'm trying to do this myself in a lab. So let's go ahead. You know, there's 60 seconds in a minute, and there's 60 minutes in an hour. And you know, I'm going to even be adventurous and I'm going to throw this into days, because hours could be fine, but we may even need to know hours. So 24 hours in a day. So let's figure out how many days this will take us, because that's a lot of seconds, I can tell already. that we're not going to have a good time. So we take this number, 1 over 60, same as dividing by 60 seconds. Do it again, times 1 over 60, same as dividing by 60 minutes. And then again, this time 1 over 24, same as dividing by 24 hours in a day. And we get 1.837 days. So 1.837 days. If we're talking about sig figs, I'm going to put that in the appropriate sig figs. 1.8 days would be my answer here. All right, because this looks like the least number of sig figs. I know it's technically a trailing 0, but we'll just assume 2 sig figs for that. Wow, that would take a long time. Okay. So you would set this reaction up and just let it go. It takes a lot of energy to do that. Okay. All right, this time we want to know mass. How can we solve for mass? Essentially, this is an exercise in working backwards, right? We started with a mass and then figured out the time. We're going the complete opposite direction. What equation are we going to start with? Yep, C is equal to IT. We have our I, we have our T. What do we have to be careful though? What do we got to look at when we're looking at this number? It's in days, right? So if it's days, what do I have to convert it to? Seconds, yep. So if we've got seconds, days, that's 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute, and we should get, so 2 times 24 times 60 times 60, typo, I left out a 0. That's better, off by a factor of 1,000, that's not good. Okay, or a factor of 10. 172,800 seconds. So 172,800 seconds is what we're starting with. This is our time that we're going to use in our equation. Okay? Now, it's going to get more complicated. But this is a good start. We need this time. We have a key word here. Solution. Meaning that this is aqueous. So we need to look at our half reactions first to figure out how many electrons are actually being transferred here. All right. So in this case, we know that since it's solution, there's nothing else in this solution, so we can assume that our reduction reaction is going to be our Cr3 plus our 3 electrons, and we will get Cr out at the end. What else is in our solution if we don't have any other ions? Aha! Remember earlier I said water. We're going to have to pay attention to the oxidation and reduction of water. LACI, I know. So with the oxidation of water, we have to use that half reaction, the one where we end up with H+. Remember, oxidation is loss, so if we have H+ on the product side, you know you got the right one. So we've got O2 plus 4H+ and 4 electrons. Okay. So we have to go ahead and balance this. What do I need to multiply my reduction reaction by? And what do I need to multiply my oxidation reaction by? All right, times 4 for the reduction, times 3 the oxidation. We should get 4 Cr3 plus, so we get plus sign, plus 12 electrons, and we get 4 Cr. And then with our balanced equation, we get 6 H2O, and we get 3 O2, and 12 H+, and 12 electrons. So we have 12 moles of electrons in this reaction. That's where we're going to run into some issues with our dimensional analysis, because we have to make sure we account for all of those electrons, right? So we got to use our conversion factors there. We know that our time that we have here in seconds times our current, 7.60 amps times 172,800 seconds is going to be equal to our coulombs. So this times my current, which is 7.6. Oh my gosh, large number of coulombs. It's a million, just over a million coulombs of charge. So 1313280. So 1313280 coulombs. All right. Now we have to do our big conversion step. Again, we're not rounding anything till the very end because we'll account for sig figs then. All right, I want coulombs to cancel. What number should I use? Well, you said Faraday's constant, 96485 coulombs. Remember, we're going in the reverse direction this time. So coulombs are on the bottom because that would cause them to cancel. And we'd be left with moles of electrons, right? But now we got to figure out how to cancel out moles of electrons. Where should I put my moles of electrons? Well, to cancel them out, I know they have to be on the bottom. The question is, what do I put here? Well, we just spent all that time balancing. Our coefficients are going to come in handy here. So we know we have 12 moles of electrons in this reaction. And what are we trying to find? We need to know moles of what? Trying to find the mass of chromium that's solid, so we need to figure out the moles of chromium that's solid. So if we're doing mole to mole, 12:4 ratio, we need 4 moles of chromium in this reaction to get us there, right? Now that we're in moles of chromium, I can convert into my grams of chromium. So I need to use my molar mass of chromium, which is 51.99 grams, and I should be able to get my mass. I want to use 3 sig figs for this because I've got 3 sig figs here and 3 here, so that is going to be my smallest amount, is 3 sig figs. So let's take that number, that big number, we're going to multiply times 1 over Faraday's constant, 96485. That was our fraction. And then our next fraction was 4 over 12, 4 moles of chromium for every 12 moles of electrons. And then we're going to multiply again by our molar mass, 51.99 divided by 1. Okay. And we get 235.88 grams. 235.88 grams. If we account for sig figs, this becomes 236 grams of chromium. So that's cool. That's a lot of chromium. But again, think about the time. It takes 2 days to get this much chromium. Yikes. So we've got these two problems here. What reaction will take place at the cathode and the anode when each of the following is electrolyzed? All right. So here's where we have an issue, because when we are looking at our slides, we'll go back to our slides for a second, we have KF. So if water is present, we have to figure out which is getting reduced and which is being oxidized. Looking at a rule of thumb, we do have a lovely group 1 element here. We have potassium. Potassium will not be reduced in this reaction. We can assume that water will be reduced instead, but let's prove it with the numbers, okay? So for a question like this, we need to look up the half reactions of K being reduced and F being oxidized. And while we do that, we also have to compare those things to the oxidation of water and the reduction of water. Essentially, we're splitting it down the middle and seeing what's happening where, and we're looking at the cell potentials to help us figure it out. So on your table, if you pulled up K, if we look at the reduction side of things on this side and the oxidation side, we should be able to pull this apart. So I'm going to compare my reduction of potassium, K plus, and my half reaction is K plus and 1 minus, and I would get K out of it. The cell potential here is not very favorable, but it is a negative 2.92. And then when I look at water, I want to use the reduction version of water that I talked about, the 2H2O, and that gives you, the reduction potential is 2 electrons, sorry. I get 2 electrons, and I get H2 and 2OH minus, okay? And then if we go back to our table, I know I wrote it down over here. For the reduction value, it's negative 0.083. Okay. So E is equal to negative 0.83. Okay. So as with all reduction potentials, the one that is more positive is the one that's going to get reduced. We see that when we compare these values, water is more positive. Therefore, for A, this is the reduction reaction that will happen. Water will be reduced at the cathode. So for A, water reduced at the cathode, I'm going to write just H2O to save time, sorry. H2O reduced at cathode, at the cat. And then we want to look at the other side. The other side is our oxidation. So here we have to look at F minus. We're given the half reaction F2 plus 2 electrons gives us F minus. We have to remember that's a reduction potential from our, and a reduction half reaction from our table. So if we flip it, we can see that F minus will become F2 plus 2 electrons. And I think it's 2F minus, sorry. 2F minus gives us F2 and 2 electrons. That has a negative 2.87 cell potential. And if we look at the oxidation of water, that cell potential, the 2H2O, this one is to the O2, 4H plus, and 4 electrons. So this is, sorry, this is the E value here. So this is the E. The E for the water oxidation is negative 1.23. And again, we go with the one that's more positive because that's the one that's more likely to happen. So here, water also gets reduced, or sorry, not reduced, oxidized at the cathode. So even though we have, I'm sorry, not cathode, anode, oxidized at the anode. So even though we have Ki, or it's not Ki, Kf in this solution, it actually really doesn't have much impact. When a current is applied, the water will be oxidized and reduced, so we'll get hydrogen and oxygen gas. It's actually a pretty nice separation. And that's where we get, that's how we can determine the separation of water. If there's some sort of salt in there that preferentially separates and reduces and oxidizes, we know that if water is higher up, it will go over the Ki, or Kf, sorry. Okay, let's do this again one more time, this time for copper. With copper, still the same thing, we have to look at the potentials for each. So we have to look at our ions. So with Cu2+, Cu2+ is our reduction, half reaction, going to Cu. This has an E value of 0.34, so this is already positive, so that's a good sign. And then we look at the reduction of water here, so it's the same one as before. We can look at negative 0.83. I'm not going to write out the entire half reaction because that part stays the same. Ask yourself, which is more positive? Copper is more positive. So therefore, copper will be reduced. So Cu2+ reduced at the cathode, right? So that part's easy, but now we need to figure out our anode. So with our anode, this one, now we've got Cl2. So remember, this is really 2 Cl- ions, and those Cl- ions, there is If we're oxidizing them, we're going to take our electrons away, right? So the thing that you see on your reduction table is Cl2 plus 2 electrons gives you 2 Cli. If we reverse that, then we get Cl2 and 2 electrons. Remember, oxidation is lost. So we flip them. The sign originally was 1.36. If you look on your table, it becomes a negative 1.36. All right. And if we compare negative 1.36 to our oxidation of water that was up here, negative 1.23, water is more positive. So even though we can plate out some copper at our cathode, water will oxidize at the anode. Okay. Hopefully this is a shorter play posit. I went through as quick as I could. I know you're having issues with time. If we have any questions, we will debrief in class on Tuesday. Okay. Have a great day.